carbon bonded to 4 elements forms a symmetrical tetrahedral shape. While it may look like that one side forms a sort of top of the molecule, it is important to understand that this is completely symmetrical all sides around. The white atoms represent hydrogen, and so we have here a carbon bonded to 4 hydrogens, namely a methane molecule. We then replace 3 of the hydrogens in our molecule with the first 3 halogens of the periodic table. So now we have a molecule of bromochlorofluoromethane. The thing that we are interested in about this molecule is that it is a chiral molecule, and in fact it is the simplest stable chiral molecule that we can produce in the laboratory. What a chiral molecule means is that if we were to take the molecule and create a reflection of it, as if we were putting in front of a mirror, there is no way to superimpose the 2 molecules. So we see that even though their chemical composition and structures are the same, they are different in their orientation in space, thus forming different molecules with different properties. We call these 2 molecules stereoisomers, and in fact, in this particular case, they fit an extra criteria of being enantiomers. But we will see exactly what this means later in the video. If we were now then to replace back the bromine atom with a hydrogen, and try to do the same thing, we see that we end up with a superimposable reflection, and so we have the same molecule. This shows that only some molecules are chiral and have stereoisomers. We see that this molecule of bromofluoromethane has a plane of symmetry. A molecule will only be chiral if it does not have a plane of symmetry. Though an easier way to check for chirality is to simply check the attachments to the carbon. If all 4 attachments are different, then the molecule will be chiral. Note that you must take into account everything attached to the carbon on that particular side as a whole, and not just the element directly bonded to it. For example, in this molecule, you must take into consideration the whole methyl and ethyl groups attached to the chlorinated carbon, not just the carbons adjacent. These are in fact different attachments, and so this molecule is therefore chiral, with the chlorinated carbon being termed the chiral center of this molecule. And we will see in a second that a molecule can have multiple chiral centers. This molecule has 2 chiral centers located here at these carbons. You can try checking them for yourself to see that they in fact both have 4 different attachments. We can reflect this molecule the same way we did before and create its enantiomer. Now if we take this molecule and reflect only the top chiral carbon, we make this new stereoisomer, which is not a mirror image of either of the first 2. We can then take this new stereoisomer and reflect it again to get its enantiomer. So 2 stereoisomers are enantiomers if they are exact mirror images of each other, by having all their chiral centers mirrored. If you have 2 stereoisomers which are not exact mirror images of each other, then we call them diastereomers. So in our example here, the 2 outermost molecules are diastereomers of each other, and so are the 2 middle molecules. And as we've stated before, number 1 and number 2 are enantiomers of each other, and number 3 and number 4 are enantiomers of each other. A molecule with n chiral centers will have 2 to the power of n stereoisomers, and so our molecule here with 2 chiral centers will have a total of 4 stereoisomers, which we have listed here.